Good morning, class. Today we're going to have our second lesson in our kinetics chapter. It's based on energy of reactions and using table I. So before you go any further, the first thing that we need to do is get our reference table out and have it opened up to table I. So when we're using it, it'll be easy transitions and it'll go a lot faster. Again, as the video goes on, if you want to pause, as we're using table I, just to make sure you understand what's going on, please feel free to do so. Now, when we're talking about energy of reactions, we saw in the first PowerPoint presentation that generally speaking, when bonds are made, energy is released. That we learned back in the bonding section. We also mentioned that early on in the year. We also put a vocab word to this, which we know is exothermic. So when a bond is made, energy is released, and it's called an exothermic reaction. Again, things that we already know. In general, when bonds are broken, energy is absorbed. So if I need to break a bond, I must apply energy to separate the two things out, and that will make it an endothermic reaction. So we're going to take these two concepts and we're going to apply them to reactions. And we're going to apply them in a way to understand how much energy is actually needed to make or break or cause a reaction. Now, when we do this, we're going to analyze table I. So if I pull up table I says these are the heats of reaction at 101.3 kPa and 298 K. And what those things are called, 101.3 kPa and 298 K, are standard conditions. And under standard conditions, I can look at all of these reactions and notice I have my combustion reactions up on top. I have a lot of synthesis reactions coming down the mix. And then on the bottom, I have my solution reactions, the dissociation of different salts in water. And on the bottom of table I, it says that these delta H values are based on molar quantities. So coefficient-wise, these are balanced already, but when the numbers change, the energy is going to change. We'll see that later on. And it tells me anything that's minus is going to be exothermic. And notice we have our delta H values here. Some are plus, some are minus, and some go based on what we would predict. Combustion reactions release energy. Notice negative numbers. Most of our bond formation synthesis reactions are mostly negative, but there are a few that are not. All right, so we're going to be using table I to uncover the truth about reactions and the energy needed to be released or absorbed. So on table I, we know that if delta H is negative, that's exothermic. We just saw that. When delta H is positive, that's endothermic. We saw that. Well, we're going to put to these words their simple definitions. Exothermic release heat, endothermic absorb heat. And again, this is something that we've learned by where the word energy is in a reaction. If energy is on the left, it was endothermic. If energy is on the right side, it's exothermic. So we can understand how this process works. Now, because we want to quantify the amount of energy, we need to understand that it's based on the moles of reactants and products used. So we have to use table I and compare carefully the reaction given to you to what's on table I. Sometimes you're going to see the reactions written exactly the way it's supposed to be. Sometimes it's going to be written differently. It's going to be written backwards. Sometimes the number in front of a formula, the coefficient, is not going to match. Well, when these things don't match up exactly, there's some extra steps involved to understand how table I works. When we look on table I, we saw that table I has the delta H values for all of those reactions. Remember from our previous presentation, delta H is the change in heat, and that vocabulary-wise is called enthalpy. But delta means change, H means heat. It's a change in heat. So there must be some mathematical representation, and there is. When we calculate delta H, what we're actually doing is taking the heat of the products total and subtracting it by the heat of the reactants total. That gives us our overall delta H of the reaction. And as we saw, if it was negative at the end, it's exothermic. If it was positive, it's endothermic. Very simple calculation to do. And yes, we will need this later on in this topic. For now, we're just looking up answers, but later we'll have to calculate what these things actually are. Now, when we're doing delta H calculations, it is very important to any chemist or teacher that's planning to do an experiment or a demonstration. If I know a given reaction is extremely exothermic, we cannot do it in the classroom. I would have to do it outside or demonstration. If something was going to get really, really, really cold, I need to know that the glassware that I'm using can withstand these extreme temperatures that we would get. So there is very important information that we get from this. Now, when we go to table I and look at the delta H values under standard conditions, we have two examples. Okay, so let's focus our attention to this first example. So I need to find this reaction on table I. So let's go to table I, 2CO gas plus O2 gas. Notice right here, 2CO gas plus O2 gas gives me 2CO2 gas. Notice it's written exactly the same. So that would be my delta H. It's negative 566 kilojoules. So this reaction is written as is. So I know it's exothermic with negative 566 kilojoules. Simple as that. Let's take a look at the second example. I have 2NO gas plus N2 gas. 2NO gas gives us N2 gas plus O2 gas. Let's check that one out. 2NO, N2O2. Well, notice right here. But wait a minute. It's not written exactly the same way. On table I, the N2 and O2 are reactants. The example, they're products. So what does that mean? It's not written as is. It's written backwards. So what we do with table I when things are written backwards, very simply, we take the sign that's there and we flip it. So if I go back to table I, this reaction, notice, was positive 182.6, showing it's endothermic, when the N2 and O2 are on the left. So they're on the right, and look, all we do is flip the sign. All right, simple, easy things to do in terms of using table I. Okay, now again, most of the time the questions are just like that. Other times they involve a little bit more work using some math. But either way, easy questions. Now, let's take a look at another type of question that we can use table I for. It says here, in the reaction below, how much energy would be released if 1.5 moles of O2 were used? Now, notice the reaction that they gave us, O2, I highlighted so it matches, is not 1.5 moles. So when we get a question like this, I need to do three things. First, I need to look up the reaction. I need to know, is it written the same or not? And I chose this reaction on purpose because we used it already, so it'll be easy to find again. If the reaction is written the way it is, I know how much energy it's going to release or absorb. But I need to compare the numbers that are in the reaction to the number that's asked about in the question. Notice that this has a 1 in front, but the question's asking about 1.5. So when that happens, I have to set up a proportion and solve using my coefficients. It's similar to what we did in topic 3 with our mole-mole stoichiometry, but this time we're dealing with energy. So let's analyze this problem with these 3 steps and take it through the process. So first thing I'm going to do is look up this reaction on table I. Again, 2CO plus O2 gives us 2CO2. Well, that was the same one we looked at before. It's right here. So I know that this reaction is written as is. It matches. And the negative 566 is for when 1 mole of O2 reacts. And that's why it's exothermic. Well, the question said we have 1.5 moles. So I can set up a proportion based upon what table I tells me and what the question is asking. So if 1 mole of O2, when it's used, gives us negative 566 kilojoules, well, then I can set up a proportion. 1 mole over that energy is equal to, well, if it's 1.5 moles, let's solve for x. Okay, so once we get here, again, you should be on mathematical cruise control, cross multiply and solve for x. So when 1.5 moles is being used, well, that's going to be negative 849. So that's 1.5 times this number. Again, not a hard process to carry out, but you have to make sure you put the numbers in the right spot. And more importantly, use the correct numbers from table I. Again, you may want to watch this problem one more time before you go on. Feel free to do so. But I'm going to move on to our second example of 3. In example 2, use the reaction below. How much energy would be absorbed when 0.2 moles of H2 react? So again, I highlighted H2 because that's the question we're going to be looking at. So step 1, I have to look this up on table I. So H2 plus I2. H2 plus I2, H2 plus I2, right here. So H2 plus I2 gives me 2HI. It's positive 53. So is it written the same way? It is. So I know by looking up on table I, it's written as is. So for 1 mole of H2 used, it's going to absorb 53 kilojoules of energy, making it endothermic. The question, though, says 0.2 moles. So now I set up my proportion. 1 mole gives me positive 53. I have 0.2 moles in my question. I solve for x. So cross multiply, solve for x. I get 10.6 kilojoules, which makes sense. Here I have 1 mole getting this amount. I have 2/10 of a mole. So I have 2/10 of the energy. Nothing too crazy mathematically. Again, you may want to watch this example over again to understand the process, follow it through. The third example, it says, using the reaction below, how much energy would be released when 1 mole of C reacts? So I have my reaction. So table I. I have C right here. And this time I left it alone. So you have to carry out which C I'm looking for. This is the C we're looking for. So table I, I'm looking for C2H2. So C2H2 up right here. And notice that 2C plus H2 is on the left. C2H2 is on the right. It's positive 227.4. This one is written backwards. So, like we did before, if it's written backwards, I'm going to flip the sign. So my delta H is negative 227.4 for 2 moles of C. Okay, the question says we have 1 mole, so we have to set up our proportion. So 2 moles will give me the negative 227.4. I want 1 mole instead. What's my energy? Solve for x. Cross multiply, and I get negative 113.7 kilojoules, which makes sense. 2 moles gives me 227.4. 1's going to be half that amount, and it is half. Again, easy questions using table I. Very easy to do. Just make sure you follow the process and look up the right reaction. Now, before you go and do your other examples, I just want to give you some other information with table I that we could have used in solutions, but I chose to leave it until now. If we go back to table I, on the bottom, you get your solution reactions. Notice these are the ones that have H2O over the arrow. So sometimes you're going to get a solutions question with table I. They'll ask you how much energy is absorbed or released when this salt dissolves in water. Well, whenever it says energy absorbed or released, I'm going to go to table I. But also it says salt dissolves in water. Notice these are all ionic salts and they're dissolving in water. Okay. A relationship to acid base, notice we have our neutralization reaction down here as well. And that's why when you mix an acid and a base together, it does get warm because it releases its energy. Okay, so that's a little side piece that we could add in when we start practicing Regents questions later on. All right, so now it's your turn. As always, you're going to do the worksheet that I attach. Good luck and stay safe.